So in this fourth video in this little sequence on revision of AS Further Maths matrices work, I want to have a look at this example question that you can see there. Just a couple of reminders at the beginning of this as well, thinking about identity matrices and inverse matrices. And the point here is that this example is going to hopefully illustrate what I've talked about so far, multiplying matrices together and determinants and inverses and that kind of thing. So remember that the point of finding an inverse matrix is that it is what matrix is necessary to multiply the original matrix by in order to achieve the outcome of the identity matrix. So that's this bit up here. M times its inverse is going to give me the identity matrix. Remember, identity being ones on the leading diagonal and zeros everywhere else. Notice that it, although the order of multiplication of matrices generally matters, in the case of a matrix and its inverse, it doesn't matter. I can either post-multiply like I did in the first one, or pre-multiply like the second one, by the inverse of M in order to achieve the same outcome of the identity. The other thing to remember about multiplication is that although the order in terms of left-right is important, the order as in if I've got more than two matrices to multiply together, the order in which I pair them up is not important. So that's the second part that I've got here. So if I wanted to take three matrices and multiply three of them together, A, B, C, doesn't matter whether I do A times B first and then multiply by C like that, or multiply B and C together first, as long as the A that I multiply them then by is in the correct position compared to the original list. So pre-multiplying the BC outcome by A would be absolutely fine. Notice that if I did BC first and then post multiplied by A, that would not work. Okay, so let's have a look at this example. So I've got A and B, two non-singular 2x2 matrices such that BAB is the identity matrix. I need to prove something about A. So what I'm going to do, this statement up here is a given for us, BAB is equal to I, so I can use that perfectly happily because that's been given to us as part of the information in the question, set up of the question if you like. And essentially what I want to do is I want to make A the subject of something to do with B. So I'm thinking about this a little bit like finding, sort of rearranging a formula or an equation or something like that. For example, if these were just ordinary, algebraic processes, just numbers or variables representing numbers, if I had x, y, x equals 1, because I, the identity matrix, behaves a little bit like 1, what I would do would be to divide by both of the x's on the left, to divide the whole equation by both of the x's that I can see multiplying the y on the left. And I would get y is equal to 1 over x times x, or x squared if you prefer. But with matrices, I don't know how to divide. So instead of dividing, in fact, it's not that I don't know how to, it's just that it's not defined. Rather than dividing this BAB equals I statement by B and then by another B, what I have to do is I have to multiply by the inverse of B to remove it from the left-hand side instead. And if I do it on the left, I have to do it on the right as well, so of the equation. So let's start with that statement, BAB equals I. Now, if I want to remove that first B from the list, what I need to do is to pre-multiply the whole thing by B minus 1. So B minus 1 BAB. And if I've pre-multiplied by B minus 1 on the left-hand side of my equation, I need to pre-multiply by B minus 1 on the right-hand side as well. So that's equal to B minus 1 times I, although, of course, it wouldn't matter when I'm multiplying it by I because I is the identity matrix and doesn't make any difference anyway, but I should do it to maintain correctness, I suppose. So now I have 4 matrices on the left being multiplied together, and I can pair them up in any ways I want to. I'm going to pair them up in this case as that pair. Oops, that pair to begin with. And I want to think about that because I know that a matrix multiplied by its inverse, either way around, is going to give the identity matrix. So IAB. And I know that on the right-hand side, B minus 1, the inverse of B multiplied by the identity matrix, well, that multiplying by I doesn't make any difference, so I can just have that as B minus 1. And in fact, I can remove the I from the left as well, can't I? So AB must be equal to B minus 1. And now, so that's removed one of the B's from the left-hand side of my original equation. Now I need to remove the second. Now I can't pre-multiply on the left by another B minus 1 because that would now be multiplying the A. So I need to post-multiply now by an inverse of B. So I'm now going to have A, B, B minus 1. And then I need to multiply on the other side of the equation, on the right-hand side. I need to post-multiply there as well, B minus 1 there. And now I can think about these two as the pairing combination that I want here, because they will get replaced by an I. So A times I is equal to B minus 1, B minus 1. And then finally, I know that multiplying any matrix by the identity matrix doesn't change it. So A must be equal to B minus 1 times B minus 1. As required by the question. So part B, we're given values for the entries in the matrix B, and we've got to work out what the matrix A is. So 2, 5, 1, 3. 2, 5, 1, 3. And in order to find A such that BAB is equal to I. So I can take my result from part A of the question, and in order to work out the matrix A, I just need to refer to that. So by part A of the question, A must also be equal to B minus 1, B minus 1. So I'm going to need to work out the inverse of the matrix B. And the first thing we need to do when we're working out an inverse is to find its determinant. So let's get det B. So multiplying the leading diagonal, 2 times 3, subtracting the product of the other diagonal, 5 times 1, gives me a determinant of B, which is 1. 6 take away 5 gives me 1. That's nice because I know that when I'm working out the inverse, I've got to have a fraction in front of my rearranged matrix. But in this case, the fraction is going to have a 1 on the bottom of it, so it's not going to cause any difficulty. So I can just blast straight in and calculate B minus 1, or write down what B minus 1 is. I am going to put that 1 over 1 there, just so that the person reading the work knows that I've remembered that I need to do 1 over the determinant there. Of course, it's not going to make any difference. And then the leading diagonal entries get reversed, 3 and 2 instead of 2 and 3. And the signs of the other diagonal get changed, so minus 5 and minus 1 there. And then I can do without that fraction in the front there. So 3 minus 5 minus 1, 2. That's my inverse. And then to calculate A, all I need to do is multiply 2 of these together. So 3 minus 5 minus 1, 2 times another 3 minus 5 minus 1, 2. And across the rows of the first matrix and down the columns of the second matrix, 3 times 3 plus minus 5 times minus 1, and so on for the other positions. I'm not going to fill all of those in there. You can see how that's going to work. And so that's going to give me 3 3s are 9 plus 5 1s are 5. So that's going to give me 9 plus 5 is 14. Top right, I'm doing top row times right-hand column, so 3 minus 5s, and minus 5 times minus 2, that gives me minus 15 plus minus 10 is minus 25. Bottom right comes from bottom left comes from bottom row and left-hand column. Minus 1 times 3, minus 3, plus 2 times minus 1, minus 2, gives me minus 5. Bottom right comes from bottom and right, so minus 1 times minus 5 gives me 5, 2 times 2 gives me 4. Add them together, gives me 9. And there is my matrix A, 14 minus 25 minus 5, 9.